Hello everyone, my name is Haibo Wang. Today I'd like to present a paper titled Randomized Error Removal for Online Spread Estimation in Data Streaming. The co-authors are Chaoyi Fermi, Shigang Chen, Jih-Kwon Peir. We are from the Department of Computer and Information Science and Engineering, University of Florida. First, let's consider the traditional data stream model. A data stream can be modeled as a sequence of data items. We give an example of D1, D2, D3, D2, something like that. The statistics in the data stream model include the frequency of data item. It is defined as the appearance of each data item. In the example, the frequency of data item D2 is 2 because D2 appears twice. And the cardinality of the stream is another statistic. It is defined as the number of distinct items. In the example, the data stream, the cardinality is 3 because there are totally 3 distinct items. The traditional data stream model cannot provide detailed statistics in many sophisticated applications. Let's consider the example of detecting DDoS attacks. In DDoS attacks, multiple malicious hosts launch requests to a server, preventing the server from serving normal requests. To detect DDoS attacks, for each destination IP address, we need to find the number of distinct source IP addresses that contact the destination IP address. However, the traditional data stream model cannot provide the detailed statistics. We need a more general data stream model. In the general data stream model, we first define the terminology of flow. It is a substream. In the example, the packets that carry the same destination IP address form a flow, and another terminology is element. It is data items that are distinguished by the element ID. In the example, the element ID is source IP address. In the definition, each item is abstracted as a pair F and E, and we have a new statistic, which is flow spread. It is defined as the number of distinct elements in flow. The problem this paper studies is to estimate the per flow spread in the data stream, subject to 4 requirements. The first is low query overhead. It is motivated by the fact that many applications, such as DDoS attacks, detection requires immediate response to flow spread query. The second requirement is high estimation accuracy. The third is memory efficiency, because many measurement modules are implemented in on-die memory, which is limited. The fourth requirement is high recording throughput, because data items may arrive at a line rate. Then next, we explain the limitation of prior work. A naive solution is to assign each flow a single flow spread estimator. A single flow estimator is to estimate the spread of one flow. Its data structure can be generalized as an array of m units. The units type can be different depending on the estimators we use. For bitmap, its data structure is an array of m bits. For hyperlog, it is an array of m 5-bit registers. The limitation of this naive solution is that memory consumption is very large. Considering 1 million flow, if we use bitmap, it will be 5,000 megabits. If we use 1 million hyperlog, it would be 640 megabits. So this paper considers sketch-based solutions that is sublinear to the number of flows in memory consumption. The sketch-based solutions are usually based on estimator sharing. We first consider the solution 1. The solution 1 is plotted in the figure on the right. It uses an array C of estimators and hash F to one estimate. The shortcoming of this solution is that it has estimation error due to the hash collision. In the figure, it is F prime and F prime prime. The second solutions use D arrays instead of one array. So for each array, it hash flow to one estimator, and it takes the minimum one as the spread estimate. These solutions had a trade-off in terms of estimation accuracy. On one hand, when we use minimum value, we can potentially reduce the error. However, on the other hand, if we use d-arrays, we are potentially increase the average error in each estimator by d-folds. So this is the trade-off. Another effect is that if we use d-arrays, we increase the recording and the query overhead by d-folds. So let's introduce our baseline solutions. Our baseline solutions is called randomized sketch, abbreviated as RSKT. Its data structure is a two-array estimator, C and C bar. Our algorithm is that for each flow, we first hash it to a pair of estimators, CHF, C bar HF, and then further record it to one of them with equal probability. For other flows, like F prime, the errors, these flows will also have equal probability to go to either estimators. When we query, the difference between these two estimators is the output. This solution has positive effects and negative effects. For positive effects, we can potentially evenly split the errors from other flows and produce unbiased estimate. However, this is ideal. The negative effects is that the estimate of F will be ruined if flow F collides with a large flow. Let's see in the figure that if F prime is a large flow, then no matter which estimator it goes, the estimate of flow F will be ruined. So we can also use d-array to mitigate this effect. However, our experiments show that it will not have a significant improvement. So we print our improved version. It is called a unit level randomized sketches, abbreviated as SKT2. Our main idea is that we break estimator into pieces. The piece now is unit and perform unit level randomization. Let's see the figures on the right. For each F, when we record F, we construct a logical estimator LF. The ith unit of LF comes from either CHFI or C bar HFI with equal probability, and the remaining units form another logical estimator L bar F. When we query, we do subtraction between value of LF and the value of L bar F. The effects of this design is that for any flow, no matter it is small or large, nearly half units will belong to LF and another unit will belong to bar LF. This allows the F prime will cancel the error itself. Finally, we print the experimental results. We compare our solutions with count mean best solutions, and we replace the counters with the single flow spread estimators and other benchmarks like C-sketch and B-sketch. We use different kinds of single flow spread estimators like bitmap, FM, hyperlog. Our implementations are based on CPU, GPU, and FPGA. We use two datasets, one real-world traffic trace from Peir and one e-commerce dataset. Our performance metrics can be categorized into three groups. One is estimation accuracy, one is recording throughput, one is the query throughput. We first give the estimation experimental results in estimation accuracy. We only provide the estimation accuracy results on the dataset and when we're using the plugins of hyperlog. The experimental results show that our solutions, especially RSKT2, outperform existing ones significantly. And the results on recording and the query throughputs show that our solution, improved solution, RSKT2 is the best in terms of recording and query throughput. And that's all. Thanks.